All right. Hello, everyone. Good evening. Thank you for joining us. We have another tech community virtual session. This is set up by the Hyderabad Council. We have Sindhuja here with us. Sindhuja is a software developer at JP Morgan Chase, and she's also a very active part of our Hyderabad Volunteer Council. And they are the ones that have organized this series of events. And I'm going to give it to Sindhuja now to please talk more about the series of events, and then please continue the session.
Yeah. Hello everyone. A very good evening and a warm welcome. So today's session is part of the first session. We have planned for something much bigger for the community, which we are calling it as Knowledge Cafe. Knowledge Cafe is planned as a series of tech talks over the next few months, over this year, for all our Hyderabad community folks, where we will bring in speakers and ask them to speak on multiple topics, be it not just on the tech side, be it on the career leadership side, on product management, so on and so forth. So hoping to see all of you there as participants and even as speakers. So yeah, so before that, yeah, I just wanted to give you a small introduction for the Knowledge Cafe series, which we are planning. So today is the first session. We're planning it every second Thursday of the month. So please, looking forward for speakers. We will be posting a Google Sheet in our Hyderabad community WhatsApp group. So please do enroll yourselves for whichever topic you're interested in to speak. Yeah. So let's get started. Today session is all about RAG or Retrieval Augmented Generation. This is how modern AI systems use to deliver context-aware, accurate, and intelligent responses. So before I begin, just a temperature check within the team. So very simple observation, like I know all of us have definitely interacted with systems like ChatGPT, Gemini, or other AI assistants. They can explain concepts, summarize articles, even generate code and hold fairly and like they can hold fairly natural conversations. At first glance, this feels almost magical. But the more we use the systems, we notice something important. Like something is missing. They're very impressive, I agree. But they are what? Like, can you can the community pitch in here? Like, what are the loopholes or what are the disadvantages you've found when you're talking to a ChatGPT model? Okay, very. This is very silent. Looking for answers from all of you. Hallucination, yeah. Lack of context, absolutely correct. Yeah. And also, one more thing. They're very impressive, but they're not always reliable, as answered in the chat. Sometimes they give outdated information. Sometimes they do not know private or info, like organization specific knowledge. And sometimes they simply make things up, but they're very confident while answering back. So that gap between fluency and factual reliability is exactly why the reason RAG has come into picture. So in this presentation, first we will talk about what are LLM models and then why they need improvement. Then we will talk about how RAG works and the different types of RAG and also how we can make RAG better, the frameworks and tools available to enable us with RAG pipelines, the challenges and future directions. And finally, I've prepared a very small demo, which I want to show all of you. So let's get started. First, I would like to start off with what are LLMs? It's a very foundational thing. Large language models like GPT-4, which we see even, I think the latest one is GPT-5 Omni. So the ones which we see on our open AI box at the top left corners, they are primarily deep learning models and they are trained on massive amounts of text data. They learn from books, articles, websites, code repositories, and many other text sources. Because of this large scale training, they become very good at understanding language structure and they generate very fluent responses. If you see, it's almost like you're talking to another human. Now, when we say that they understand language, we should be very careful while we are passing that statement. They do not understand in the human sense. They do not have human reasoning, a personal experience like all of us, or common sense in the way we do. What they do is they statistically model language. It's a very mathematical approach they take. They learn patterns from words, phrases, and structures which tend to appear together. If I have to simply put it, I would like to say if I ask you the capital of India is, most of you will immediately think of New Delhi, of course. But a language model also does something similar, but at a very massive scale and with much more contextual awareness. It predicts the next token based on the patterns it had learned during training. So, under the hood, LLMs basically use transformer architecture. So I do not go much deep into transformer architecture and attention mechanism in this part of my PPT. But yeah, so just to throw a light, the key innovation here in an LLM is the attention mechanism, which allows the model to look at different parts of the input we feed it and then determine what is the most important for generating the output. That is why they can maintain context across long passages and produce coherent text. I'll give you a very small example from my personal experience. Around 2016 or 17, when like I was 18, 19, I think, when I was interacting with Siri, I'd asked it a question. It had answered me back. And the next time when I asked something related to the first question, it did not have that context. That's what GPT spot in. That's what like LLM models spot in. And another thing which makes LLMs very, very powerful is that they're very general purpose. You can use it for literally anything to schedule your day, to write a complex enterprise grade application. The applications are really vast. The same model can answer your questions about cooking to answer your questions about very complex JavaScript codes. So it can draft an email for you. This flexibility is one of the main reasons LLMs became central to our modern AI architecture. But there are also some limitations, which we talked about. Even though they're very, very powerful on their own, they on their own might not be like the best for modern real world applications. So as mentioned here, the first limitation is static knowledge. A model only knows what it has learned during training, right? Like if a new information appears after training, the model will not automatically know it. For example, if my company has updated my leave policy just yesterday, or my bank has changed the interest rate this week, a standalone LLM model might be still using older information. I don't know if you remember, but like in the early days of OpenAI's ChatGPT, which came in, there used to be a banner at the below saying that my knowledge is limited till 2021. So if we had asked it who is the president after 2021 of the United States, it would not know. So that was a generic basic LLM model without no external information or external knowledge base connectivity. And that's when the static knowledge limitation came in for a standalone LLM model. The second limitation is, of course, hallucinations. This is the most discussed term when we talk about issues with LLMs. Hallucination means the model generates information that sounds very correct, but is actually false. It may invent references, create facts that do not exist, or combine pieces of truth into something inaccurate. This is especially very dangerous in domains like healthcare, finance, where precision matters. Like, of course, you don't want it to tell you that you have another disease, like when you actually don't have anything, right? And the third limitation is lack of access to private information. A public LLM, of course, does not have access to domain specific questions or company specific knowledge. So yeah, so morely like the third and fourth limitations mainly talk about access to private or enterprise level data, and lack of domain knowledge, like specialized terminology, compliance rules, organization specific workflows, etc. So I can give you an example. So if you ask a banker should not ever answer a question with just financial knowledge. He should know what his company is doing, how much are they charging, very, organization and institution specific policies and operational rules. So the important thing we need to learn from here is LLMs are fluent. We totally agree. But fluency is not the same as reliability. In many cases, especially enterprise level use cases, what matters is not just generating an answer quickly, but generating the correct answer using the correct source. That is why we need a mechanism to connect LLMs with an external knowledge. And that mechanism is RAG. So, first, let's talk about why RAG, and then we will move to fine tuning versus RAG. So, RAG, of course, stands for Retrieval Augmented Generation. It combines two things, very simply put. There's retrieval, there is generation. Retrieval means fetching relevant information from external sources, and generation means using a language model to produce the final answer. This is important because instead of forcing the model to rely purely on what it is stored in its parameters, we allow it to look up relevant information at runtime. That is when a user gives a query. So when a user asks a question, the system first retrieves the most relevant knowledge from a knowledge base and then uses that knowledge to generate the answer. Of course, in this case, the precision is going to be more. Uh, if I have to compare, I can maybe give you an analogy like this. Let's take one student who answers purely from memory, another student who is allowed to use a textbook like an open book exam, and a third student not only uses a textbook but also checks multiple sources and reasons with them. So if I had to compare these three, a plain LLM is like the first student. A basic RAG system is like the second student who has access to a knowledge base. More advanced RAG systems start to resemble the third student. So why is RAG even valuable? Because it improves factuality. It makes our AI system more reliable and factual. It reduces hallucination. It allows the system to use very recent information, and it makes the system more useful in even domain-specific environments, such as legal firms, hospitals, universities, etc. So, for example, if I'm asking a customer support assistant, what is the current international roaming charges for my plan? The information, of course, changes often. A standard LLM might guess based on the general patterns, but a RAG retrieves the latest document and answers from that. That's where precision and accuracy comes in. So the real power of RAG that it turns is that it turns an LLM from just a general language engine to a very context-aware knowledge assistant. So far, I just want to take a pause here. Any questions before we move on to, I'll just check the chat. Any questions, team, or we are good to go? Okay. Let's jump to the next topic. So, if you can see the meme which I presented on the screen.
Sindhuja, I believe there's a question for you in the chat.
Okay. No. MCPs are a little different from RAGs. MCP stands for Model Context Protocol. That is more about collecting all the context, like whatever we are feeding to the RAG, collecting the context of, let's say, your company has a lot of Google Docs. So collecting it to a single context, which we feed to our RAG as a knowledge base, comes under MCP. I hope I answered your question, Manikanta. Yeah. Okay. So if, as you can see the meme on the screen, there's an AI engineer who wants to build a production LLM app, and he has to choose between RAG and fine tuning. So let's talk a little about RAG versus fine tuning. In a practical sense, many people confuse RAG with fine tuning. So what does fine tuning actually mean? Fine tuning means taking a pre-trained LLM model and training it further on domain-specific examples. This changes the model's weight. It can help the model adopt a new tone, a new style, a new vocabulary, or very task-specific behavior. But RAG, on the other hand, does not modify the model weights. It leaves the model as it is, but it gives it access to relevant information during inference. So the difference is very simple. Fine-tuning will change what the model has learned internally, whereas RAG supplies it with information externally. Very useful rule which you can keep in mind when you have to answer RAG versus fine tuning is, if the problem is about knowledge, we use RAG. If the problem is about behavior, tone, or style of a task, fine tuning will help. Very simple. For instance, when you're talking to a doctor, how do you want him to speak to you? You want them to speak in a very soft, empathetic, calm tone, right? So, but when you're talking to a chatbot, if it's very harsh to you, it doesn't make sense. So changing the tone, behavior, or something can be done, like changing the tone or behavior can be improved by fine-tuning of a LLM model. Current procedures like what is the latest insurance policy, so on and so forth, can be handled by RAG. In practice, I feel that strong system should combine both. It should not be a this or that. It should be both. And another important difference we need to talk about is update cost. If a company policy changes every week, it is not practical to keep fine tuning the model every time. With RAG, you can just supply it with the latest information on the knowledge source or the knowledge database, and the system will retrieve the latest version. That is why RAG is often preferred in environments where knowledge changes very frequently. So we've spoken about RAG so far and RAG versus fine tuning. Let's dig a little deeper into how RAG works. Okay, I hope the slide changed. There is some lag on
Yes.
yes. Yeah. So now a very basic and simple question. How does a RAG work? As you can see here, it's very simple. Step one is I give it a question. I ask, can you please write a test case for this file for me? Step two, the system converts that question into a suitable form for retrieval. Often, the suitable form for retrieval is a vector. We will talk a little more about vectors in the upcoming slides. Step three, it will search its knowledge base. There is a knowledge base, right, where we have fed it all articles, books, newspaper articles, whatever, XYZ, textbooks, so on and so forth. It will retrieve the most relevant documents which are matching to my query. Next, those retrieved chunks are passed to the LLM model, as you can see here, along with the user's question. The language model then generates the response in a very human-like format. This will sound very simple for someone saying it, but it's very powerful. The key difference from a normal LLM to the answer that is generated now from with integration with RAG is that it is supported by actual information and it's very precise. Let us take a real world example. Suppose I have a chatbot in my company where I ask it how many days of maternity leave are available. The system should retrieve the HR handbook. It should also get all the required details and then uses LLM to produce a human-friendly answer. The model is not inventing the policy. It is interpreting and presenting the retrieved policy. So that's a very important thing we need to understand. Like RAG helps in retrieving the policy, whereas LLM model presents the policy in a very human-like good manner. This is also why the quality of retrieval matters much. If the system retrieves irrelevant information, even the strongest LLM model will produce a very weak answer. So RAG is not only about generation. In many cases, retrieval is the decisive part of this. So now that we have spoken about how RAG works and why it matters, I would like to show a very, as you can see here, it's a very small basic RAG pipeline which I've done here. So let's unpack it a little. So before we jump on to the next slide, so there is some context. We will begin with documents, which are, let's say, 3, 4 PDFs. They could be PDFs, they could be reports, they could be contracts, policies, textbooks, support tickets, emails, web pages, anything you wish. In enterprise grade applications, they are usually internal knowledge, like company specific knowledge sources. Next comes chunking. Of course, large documents, millions or billions of GB, is too big to retrieve or feed directly to the model. So we chunk it up, like we break it into parts. This is also important because retrieval works better at like smaller chunk level than the full document level. For my model to read the full document only, it might take a lot of time, which will also delay my response time. Then we generate embeddings for those chunks. We'll talk about embeddings in the next slide. They are nothing but, like, if I have to put it simply, embeddings are just numerical representation which show us what the chunk means. So these embeddings are then stored in some database. We have to store them definitely. And at query time, when a query comes in, we also embed it and then just match. It's just match the following of embeddings. And I retrieve the top K most similar chunks. So this is a very simple baseline system. And that's why it's called vanilla RAG. So this is how RAG works. Now that we have spoken about spoken about RAG and how it works, let's dig a little bit deeper into what are vector embeddings. Before coming to vector embeddings, I want to mention one point. In the previous slide, when we spoke about breaking down huge text into small chunks, we need to note that the choice of the chunk size is also very important. It can affect the quality of whatever data is. If chunks are too small, there is no context, like it will just be one sentence. So it doesn't know what is the context of the other, what is the context for it. And if they are very large, there might be some irrelevant information. And also there is a chance that the response time is hugely increased. So even in a simple pipeline, design choices matter the most. Now, let's quickly jump into vector embeddings. Vector embeddings, as I was telling, are the core building blocks of RNG. They are just, but like to put it very simply, in childhood, we have learned of matrices, right? They are just some list of numbers, something like this, if you can see. Very simple, just numerical data. I don't think like as humans, we understand this, right? So they are numerical representations of text or any other form of data. In this case, I've shown text, but it can be an audio, it can be a video. And there are some models which are present like BERT, word to vec, which convert the input data into embeddings or vector-like format, vector data. So it's very simple. The goal is that the text with similar meanings should end up close to each other. So, for example, car and vehicle should have similar vector representations, while car and banana should be very farther apart. This allows the system to reason about similarity in meaning, not just exact word overlap. This is a major improvement over traditional databases. In keyword search, if I search for salary policy, it will go to the DB, search equal to salary policy. Yes, retrieve. No, just leave it there. But that's not what I want. If I'm searching for salary policy, I want something in the context of compensation guidelines or something like that. They are similar. In fact, they are the same. So with embeddings, that semantic relationship can still be captured. So embeddings are very useful in RAG because user questions and knowledge-based text may use different wordings for the same concept. Embeddings will help bridge that gap. From a technical perspective, embeddings are of course generated by embedding models like BERT, BERT2Vec. These models may produce vectors of size 384, 768, 1024, depending on the model used entirely. Those numbers represent dimensions in vector space. For example, if you see like embedding 1 could be fruit, like this is embedding 1. So this fruit, embedding 2 could be animal, embedding 3 could be color. So like in a multi-dimensional vector space, there is banana here, there is orange here. If you see the distance between banana and orange is less than banana and finch, something like that. And similarly, orange and yellow, like it's a little closer than orange and banana. So that kind of thing. So, and just a note, like we don't need to interpret each dimension manually. What matters is that the vector captures the semantic information so that we can compare later on. They allow these vector embeddings are mainly for machines to learn how to compare because they do not have this human sense wherein, I don't know whether compensation and salary are same. Like the machine does not know that. So for it to compare, that's when it's done. So I will take a pause here and are there any questions? Okay, so what's a vector DB? I'm going to talk about vector DB very soon, Rehanna. And Mani, how the chunking is performed. So chunking basically is done by the React frameworks by itself internally, but generally you can also define the chunk size. Like you can also define the chunk size manually. And orange refers to color of fruit. Such a good question. So in this case, like in terms of context, it depends on how the vector was generated. For example, if I'm using a model like BERT, it will it will know that orange is a color as well as a fruit. So it will generate the vector accordingly. So it basically depends on the model which we are feeding our words to, how they are performed. So hope your questions are answered, Mani and Rehanna. Rehanna will talk about vector databases in the next slide. Okay, let's move to vector databases. So now we have the embeddings, well and good, but we need a way to search and store them, right? Like search them efficiently and store them. That brings us to vector databases. A vector database, it will store the vector embeddings and it will support a very fast similarity search. Like we saw in the previous slide, right? One vector is having multiple dimensions. To search mathematically through all of them, compare all of them would be a humongous task. So vector databases are specialized for that. Instead of exact matching, it retrieves the nearest vectors to a query vector. The workflow is very simple. We convert the data into vector embeddings. We store those embeddings. When a user asks a question, we convert that question also into an embedding, and we will compare for the most similar stored embeddings. This is what large-scale semantic retrieval looks like. So how you might ask, how do they compare? There are multiple mathematical measures which are used. Like, for example, as like the most commonly ones used is cosine similarity between vectors. I'm not digging deep into the details mathematically, but cosine similarity is between basically something like the cos theta between the two angles. If there are two vectors like this, the angle between them, the cosine of the angle between them is cos similarity. Similarly, there is dot product and there is Euclidean distance. Euclidean distance basically means, for example, this is the point, this is the point for two vectors. I'm just assuming the distance between them. So that is the Euclidean distance. So you can just have a look at it, but vector databases already provide it internally. So there are some very famous vector databases like Pinecone, FAISS, Roma, Elasticsearch, PostgreSQL, so on and so forth. All these have internal indexing mechanisms as well as like each each database has one similarity measure it uses. For example, FASS, which I'll be showing in the demo, will use cosine similarity internally. First, it does an inner product of the vectors and uses cosine similarity. So these, like, vector database comes with that abstracted layer, like it gives you everything properly. So it is also very important to distinguish between a vector database and a traditional database. A normal database, as you all know, we have rows, columns, so on and so forth, and it can store blobs, metadata, timestamps, user data, etc. But a vector database is primarily optimized for storing vectors. That is the embeddings. In many practical systems, usually both are used together. For example, a normal database will store all our raw documents. A vector database will search, like will get and search those documents. So it's very important to have a good vector database because the index is what is used for the retrieval. And one more point I want to mention is that vector search has to definitely scale. Now we'll have millions of vectors in multiple dimensions. There are even vectors with 1024 dimensions. So effective indexing and approximate search, like the search of vectors, becomes very important in such cases. There is a little depth to this wherein, like we can talk a little about what indexing algorithms vector databases actually use to search so quickly in seconds. Like you ask ChatGPT a question, it comes back in 1 second or 2 seconds, basically. So internally, there must be billions of millions of embeddings. So that would be a very specialized session. So I'm not covering that as part of this session. But on a whole, if I have to summarize this slide, I would say that vector databases provide everything abstracted, especially the fast similarity search, and you can directly use them. So, okay, I'm looking at the questions. So, what is a vector DB? I've answered that question, Mubina. If the input is a large size PDS, how can we chunk it and how to define the size? It depends on, there's no ideal size, I would say, Mubina. It depends on what kind of context you want to preserve in each chunk. So that's with respect to that. How does the question gets converted to embeddings? The question gets converted to embeddings in the same way how we are converting our raw data money. Like I told you, right? There are some models like word2vec. Word2vec is the most famous one used for text. So same like how we are converting our raw text to vectors, even the question also in the end of the day is a text, right? It will get converted to embeddings. Why are embeddings better than keyword matching? Okay. So keyword matching, as I was telling before, there is an example, right? Salary compensation. If I do a direct keyword matching, it's never going to match. But vectors, like whatever embeddings which are being generated, they have some metrics which show some contextual information of that data also. Like they say that salary and compensation, the vectors, if you compare, are a little similar. So it's more for the context of that particular word or sentence. So I hope I answered your questions, Ananya. And would there be any thread lock issues in VectorDB or stale data? In VectorDB, stale data is definitely an issue. Like we need to make sure that VectorDB is thoroughly updated. Thread lock issues, I do not see VectorDBs are well handled for multi-thread environments and also for very fast retrievals. So I don't think there will be any thread lock issues. Okay, so I hope I've answered all questions. Now let's move to the next slide. Okay. Now that we spoke a little about the internals of RAG, such as vector embeddings, and we also spoke about vector databases, let's quickly jump into different types of RAGs. So I've listed like 6 RAGs here. I will quickly walk through each and every one of them. So there is vanilla RAG, which we spoke about. It's a very simple pipeline. Retrieve, generate, LLM gives you the answer in a human-like format. It's a very good starting point for prototypes, very good starting point for teaching demos, basic demos, but it has limitations. Retrieval is not precise. There is no advanced filtering. So while it is easy to build, it is not good enough for high stakes applications and enterprise level applications. So next we have advanced RAG. Advanced RAG it improves the basic pipeline. It uses smarter chunking strategies. It uses better metadata filtering. It uses query rewriting, document hierarchy awareness, and even better retrieval logic. So for example, instead of chunking into fixed sizes blindly, it may use semantic chunking that will respect paragraph wise. Like for example, it will say section 1 is talking about let's say trees, and section 2 is talking about flowers. It has that intelligence to like differentiate that this should be one chunk and this should be one chunk. So instead of treating all documents equally, it will filter based on recent documents versus very old documents or document type. So this will lead to good high quality retrieval and better accurate answers. And there is of course hybrid RAG. Hybrid RAG combines semantic search with keyword based search. So this is useful because we have semantic search which will capture the meaning, but exact keyword search is also valuable for specific terms, especially one example I can think of is legal clauses. Like that legal clause, that specific section should have that keyword matching strategy. I cannot give you a very similar, I cannot just say that this is similar so you can quote this in your quote. No, I need that keyword matching. So I would say it's better to have both semantic search as well as keyword search, which gives the best of both worlds. And this is the most common used in production applications actually. So these are very basic RAGs. Next, we have the advanced RAGs on the other side of the slide. There is re-ranking RAG. So in re-ranking RAG, the system first retrieves a set of candidate chunks. Then we use a second model to re-rank them again based on relevance judgment. So it's basically, if I have to put it simply, it's a reasoning model. So you might think, why is this needed? In the first step, what will happen? I'll go get like quickly, very quickly, I'll get all the chunks. Like 5 results, it'll get me. But are really those 5 results relevant? Is something we need to reason on. So that second model adds that careful second pass or that second eye. So instead of assuming that the first 5 are the best ones, it will refine it better and it will definitely improve your answer quality. So recently I was fixing something and I was reading through the chat Claude was giving me, and then it was saying, yeah, I did this. I changed V1 to V2, but I think I should also change this, which means it's reasoning with itself. It generated a question answer, but it is also thinking whether that answer is right or wrong, and then regenerate. So that is something I would say call as re-ranking. Similarly, there is agentic RAG. This is the hot topic nowadays. It's a very advanced one where all the there are multiple things which come under agentic RAG. It will first, if you ask it a very if you ask it a very complex question, it will break it down into sub questions. It will retrieve multiple times. It will plan the entire answering strategy. It will reason with itself. It will also see whether any additional information is needed. For instance, if I ask it, I want reimbursement policy in 2024, and you explain the main changes, a simple retrieve one system may struggle, but an agentic system will retrieve both the versions, it will compare them, and it will construct a very structured, good answer for you. This introduces more intelligence, but it's also a little complex. Next, we'll come to multimodal RAG. Multimodal RAG is very simple. I don't know how many of you have hopped on to the recent trend. There was a trend where people were generating Ghibli art of their faces, of their pictures, right? So that's when the images videos, audios come in. Like multimodal RAG concept is the idea extends beyond just text. It can retrieve and reason across images, tables, documents, audio, video. So, for example, in healthcare, we can combine the patient notes with X-ray pictures to get better, analysis. So, as the requirements become more demanding, RAG evolves from simple retriever pipelines like the vanilla RAG to a very more intelligent, richer system. So, now that we've spoken about the different types of RAGs, I will quickly touch upon RAG enhancement techniques. Let me just check if there are any questions. Okay, Anupama ma'am is answering the questions on the chat. Like first, let's complete the content and we'll come back to the questions at the end of the round. So now let's talk about RAG enhancement techniques. I think there were some questions asked about chunking. First thing is, of course, chunking is very, very important. It's not trivial. If chunks are too small, they will lose context. If they're too large, retrieval becomes too noisy. So good chunking preserves meaning while remaining retrievable. So we can use fixed size chunks. Like we can determine, like on a document of 10 paragraphs, you can say 10 chunks. That is also one way. And another is semantic chunking, which I was talking about. That is more of an intelligent chunking, wherein it will say that, like the RAG will say that first chunk is talking about our previous example, trees. Second chunk is talking about flowers. So it will chunk by itself. Next is query optimization. So for example, I ask it leave policy, but it can extend the query rewriting. Like it can rewrite the query to company leave policy rules, HR document. So it gets like better matching results. Same, right? Like if I just give a PR in Claude, it will like try to see if it has to review my PR or it has to retrieve my PR, so on and so forth. The next is, of course, hybrid search. I think we've spoken about this a little. Keyword search as well as semantic search combined. And we have also spoken about re-ranking in the previous slide, where the top retrieved chunks are reordered by the second model to improve precision. The fifth is metadata filtering. This is something which we can talk about. The filter will be based on date, author, category, recently. So it's more precise retrieval. And of course, context compression. Sometimes retrieved chunks contain too much irrelevant text. Compression techniques reduce noise and preserve only the most useful information before passing it to the LLM, so that the LLM gives a very grounded factual answer. One thing I want to talk about here, take a pause, is once we start adding these enhancement techniques, we also need to measure whether they actually help. So a good RAG architecture is not just about, the design part of it, but also testing the quality of the output. Like how is the answer changing? How is the retrieval quality changing? How is the cost changing? Or is there any increase in the retrieval time? For example, if I do re-ranking, there is another layer I've added altogether. Is it really required in my use case? So that is something definitely we need to think about before adding any kind of enhancement techniques. So that's with respect to RAG enhancements. Next, we will talk about RAG. Now we have spoken so much about multiple steps. RAG does the query, RAG does retrieval, RAG converts into vectors, it stores into vectors, it generates LLM response, such a huge pipeline. For a POC, if I have to set all of this up from scratch, it will take a lot of time. So that's why frameworks are available. That's the beauty of engineering. So everything is available in the form of a simple tool. There are some popular frameworks. There is LangChain, there's Llama Index, there's Haystack. So these are pre-available RAG frameworks and tools which help us reduce that boilerplate code and we let developers experiment very quickly. But it is very important to understand what happens beneath. Like a framework can help you implement a pipeline, but it cannot represent like the architecture understanding behind what goes in a RAG. In practice, generally, RAG frameworks are used, but we combine them with some custom logic. So that's with respect to RAG frameworks and tools. What they provide easy pipeline creation, they handle queries quickly, they support multiple LLMs, and they can easily integrate with vector databases. So that's with respect to RAG frameworks and tools. Before I jump into the demo, there's one thing I want to talk about. I want to talk about challenges and future of RAG. Let's discuss challenges first. As we were discussing in the chat and a lot of audience have asked, the first challenge is poor chunking, leading to poor retrieval. If your source is split badly, the retrieval may miss critical context of fetch irrelevant pieces. And second thing, what you feed in comes out as an output. So your data should be good enough like for a RAG to understand. The second challenge is the limited context window. Even though modern models are having better context windows, but I definitely cannot feed hundreds of documents and ask queries. So a system cannot keep passing unlimited retrieved material to the LLM. So like that is definitely that context window of the LLM is definitely one limit. It's getting improved day by day, definitely I agree. The third and foremost thing for us is latency. RAG systems need retrieval and then generation. And if you are using something like re-ranking, filtering, or agentic reasons, will increase the response time. So that is something we need to keep in mind. And the fourth challenge is cost. We are generating embeddings. We are storing the embeddings. We are using an LLM model which retrieves that embeddings. LLM calls, API calls, all these add up to the cost. So we need to do that comparison, the cost versus are we like the output we are producing. So that's with respect to the challenges of RAG. Another challenge, which I feel worth mentioning, although it's not on the slide, is evaluation difficulty. How can you evaluate a RAG model? Like you will feed it, you'll make it better, but there's no particular metric we can use to actually evaluate how accurate it is. So proper benchmarking in that area is definitely an area for development. So now let us look at the future. Agentic RAG is going to take over. I think it's already here. So there will be autonomous systems which will plan, decompose, verify, reason with themselves, fix it, everything on its own. RAG compliant with knowledge graphs. So instead of vector databases, if we use knowledge graphs, which we built, like the similarity, I think knowledge graphs in some extent also solve that orange is a color or orange is a fruit problem. You can generate the knowledge graph in such a way that orange is present in both the knowledge graphs. And there's multimodal RAG, which is already present in GPT 5.0. And there's self-learning RAG, which uses feedback over time to improve itself. So RAG is not standing still. It is rapidly evolving. That's all I can say. So let me quickly share my. So I put a very small demo actually. I hope you're able to see my screen. Can someone confirm if you're able?
Yes, we can see your screen.
Yes. So here I put a very small demo of our RAG pipeline. There's documents, there's embeddings, there's the index, so on and so forth. So this is the pipeline which I've shown in the before slide. So these are the stored documents. As you can see here, I have given it some information on the PPT information itself, like what does RAG stand for, what are vector embeddings, what are vector databases, what is chunking, fine tuning, hybrid search, re-ranking, etc. So actually, I wanted to show you how it works in real time. So this is how what happens inside the FAISS database. So there are 8 vectors, as you can see. The dimension of each vector is 384. I will show you that also. So it stores the vectors, and it does not store the raw text or meaning or understand. So there is document. This is an embedding preview. There's document 2, which is an embedding preview. I will show you the full, like what it stores in the database. See, there are 384 vectors, like 384 dimensions, which are part of a single vector, as you can see. So now, if this is a very simple RAG I've built. So for example, instead of vector database, I search for, let me search for RAG. And as you can see, I'm putting top 3 retrieved chunks as 3. So it's running the RAG. So these are what like context which I sent to LLM is this one. And the generated answer is RAG stands for Retrieval Augmented Generation. And it did retrieve 3 chunks, if you can see. Like it retrieved RAG stands for Retrieval Augmented. And as there is RAG, there is also fine tuning. And so if you can see the distance score, you can see here. The smaller, the most relevant. So it retrieved 3 chunks of data. So in my case, I'm speeding each sentence as a chunk. So this is a very simple demo I wanted to show you so that like you understand how RAG works in real time. And uh, yeah, I'll conclude and then I'm open to questions. So we have spoken a lot about RAG today. And LLMs, definitely LLM models standalone make AI capable of speaking well, but RAG makes AI capable of speaking correctly in context. And that is why RAG is very important and a very central idea. So definitely RAG is in AI, and absolutely agree with that. So I'm open to questions. I do see some questions. Yeah. So Money, to answer your questions. See, at the end of the day, image is nothing but a matrix of pixels, which is numbers again. So it can convert image into a matrix of pixels, which store that contextual information. Same with videos. Video is like an array of images, fast. Like images move fast in a video, if you see. So it will capture each image, get it in a matrix form, each pixel, and it will compare. So that's how it works for images and videos. If 2 sentences have different words but same meanings. Yeah. So how we generate the embeddings is how the context is stored, Ananya. Like the word to vec, the whole idea of vector generation is that to have that similar. Let's say I'll give you an example. Yeah, salary and compensation. Although the vectors are different, if you do a vector dot product of both, they will be very similar in the vector space. So similarly for 2 sentences, there are multiple strategies. It can store the whole sentence, like it will break it down into each word, store the vector, add those vectors, and store it as the vector for the sentence. So that's how it works for sentences. Yeah, I hope I've answered all your questions, Ananya, Mani.
All right, folks, this is the last opportunity for you to ask more questions to Sindhuja before she wraps it up. In the meantime, I'll also put just to sort of bring back to the series of events that we're doing. The Hyderabad Council, who is here present with us, along with Sindhuja, they are hosting a series of tech talks and tech sessions like this one. This is the first of the many. I'm sending an Excel sheet with the WhatsApp group here. In the Excel sheet, you can nominate a speaker. It can also be yourself. At the same time, in the WhatsApp group, you can keep an eye out for more such events. I believe Mani is asking, have you already answered this? Can you further provide differences between RAG and MCP?
Sure. Like if do you want me to do it now? I can just post it. It's a little complex topic, I would say. MCP, I would say, is more of the context we provide, whereas RAG is an entirely different mechanism of just retrieval and generation. So we will post that, like I'll post a proper answer in the group, Money, if it's okay with you. Ananya, very good question. Actually, evaluating RAG performance, as I was talking in my limitations, very difficult to evaluate RAG performance. There are some metrics, I do agree, but how far are those metrics valuable is definitely a question, is an open-ended question. There is some more research which is being done in RAG. So in evaluating RAG performance, but there is no certain way of evaluating RAG performance. Like I cannot tell you which RAG is better, like at a certain point as of now. Definitely there should be a metric which comes out.
Yeah, this is Anupama. Very thanks to Sindhuja for a detailed acting. She wanted to take time for the MCP, but being a little gray head, I would like to clear the air. See, MCP is more like your Java servers. If you have J connectors, if people work in Java, MCP is a server, it's part of the infrastructure. The reason for it is everything, whatever she explained, if people translate it to the machine learning, different machines have stored different types of information. And when you have a multimodal RAG, text, image, all may not be sitting together, right? There are pipelines you build. It's more like your textbook where you have some pictures, some text that you read. So everything, when it is translated into the machine learning, there are bits and bytes, and they are called TPUs. So if you know what exactly is the architecture, the hardware of the fine-tuning methods like the NVIDIA A100s and all, each one of them have different kind of things. So that is where the MCP servers do play a role to actually help you to scale up and perform the context for the RAG search. So it is not actually a lot of software, it's a protocol. It has different kind of things, but because the person is coming again and again, it is a very detailed explanation given by Sindhuja about the RAG from the programming perspective. It's all about the search. So MCP servers sit well when we talk about the agentic AI. I'm one of the members from the Hyderabad community along with Sindhuja. So if that is what is interested, we'll definitely have a session on the MCP servers and the agentic. Just wait till that. But to clear the air, MCP servers are, they're called servers, they're part of the infrastructure. They are more like your J connectors, which synchronize the data to clear the pipelines. That's it. A very detailed explanation, Sindhuja. Congrats to you for that kind of a details.
Yes. Thank you so
I'm
much,
sorry
Anupama.
to intervene when she's speaking, but since again and again that question coming, I just thought I will clear the air, clear the doubt.
No, that's great. Thank you so much. And big thanks to Sindhuja and also Anupama and the entire Hyderabad Council for hosting this. We're looking forward to more of these. Thank you everyone for joining. I've put Sindhuja's LinkedIn as well in case someone wants to connect and ask further questions. Like I said, the WhatsApp group, the speaker. If you want to also host a session of your own, there is an Excel there where you can put in your details and the team will be in connection. So thank you so much, everybody. Fantastic session, Sindhuja. Thank you so much.